Hello everyone in Advanced Math. I'm back and I wanted to show you a little bit today about sequences still, but a new notation that goes along with them. It's called summation notation. And the symbol that we're going to be using to show that it's the summation of a sequence is this capital letter sigma. And you might actually have seen this before, like in spreadsheet programs. This is actually the symbol that pops up if you want to add all the cells together, because this is kind of the generic symbol for add them all together. And so here's our sigma. We're going to go over what the parts of this mean, because there's numbers above it, below it, there's stuff off to the side of it. So what the number below it means. And there's usually n equals 1, k equals 1, sometimes I equals 1. That is just a variable. It can change. But whatever the number is here is your starting term. So n equals 1 is a really common thing, but it doesn't have to be the first term you start at. And so this is the term you're going to start at for adding all the numbers in that sequence. And then whatever the top number is the term where you're going to stop adding numbers together. And so in this particular one, you would be adding the first 10 terms of this sequence together. And then what's beside the capital sigma right here is the formula. We called it the general term. This is the formula for how you get the numbers that you're adding together. And so in this case, it's 2n. So if I started to make the terms of this sequence, if I started to write this out, when I put in 1 here, I'd have 2 times 1, that's 2. And then the next number I'd put in is 2. 2 times 2 is 4. So I'd have 2 plus 4 plus 6 plus 8 until I get up to the 10th term, and that's where I would stop. And if I add all those together, that's my answer to this question. So let's try to do one that is the same idea. And you notice I kind of shook up the variables a little bit here because I don't want you to think it has to be n. So I just used a k on this one. And so we're going to say from k equals 1 to 5 of the sequence where the general term is 3k plus 1. And so let's start first to just write out the terms. Now the fact that this is a sigma means when I go to write out the terms, instead of saying the first term comma, the second term comma, I'm going to say the first term plus the second term plus the third term and keep going. And so 3k plus 1 is our general formula here. So the very first term, our starting term is 1, so I want to put a 1 in there for my very first thing. So 3 times 1 is 3, plus 1 is 4, which means my very first term in this sequence would be 4. And then since it's a summation, I'm going to say plus. My next term would be 2, so I'm going to do 3 times 2 is 6 plus 1 is 7. And then I'm going to put in 3. 3 times 3 is 9, plus 1 is 10. And you might be noticing a pattern to these numbers. This is just going up by 3 each time. And so I'm going to keep going from here. And so we'd say plus 13 for our next term, plus 16 for our next term, and then plus what for the next term? Trick question. There is no next term. Stop. Why do we stop there? Look at our stopping term here. We go from k equals 1 to 5. That's where we stop. That's the end of this. And so I have 1, 2, 3, 4, 5th term. That means that's it. We're done. And so just add all these numbers together, and that's our answer to the sum. And so 16 and 4 is 20, 13 and 7 is another 20, so we got 20, 40, another 10, that's 50. Which means the sum of the first 5 terms of the sequence that's 3k plus 1 to get the terms is 50. Alright, so there's how we find the sum of a sequence. I want to try another one, and I made this one slightly more complicated. I made it less terms because the terms are going to be a little harder to figure out here. But we did something like this the other day. We have a negative 1 raised to a power. In this particular case, we've got a negative 1 raised to the n plus first power. That's going to make this what we called an alternating sequence. It's going to go back and forth between positive, negative, or negative, positive, negative, positive. We're going to check and see which one happens. So do you notice on this one, though, my starting term is not 1, my starting term is 2. So the very first thing I'm going to put in here is a 2. And so putting a 2 in here, if I do negative 1 to the 2 plus 1 power, that's negative 1 cubed. Negative 1 cubed is a negative 1. Now, what this whole part does here is just changes the positive and negative. And so our very first term is going to be negative because of this. And then I'm going to have 4 to the second power, put in 2 for all the n's, and 4 squared is 16. And so my very first term is negative 16. Although my first term here, I should say, because it's really the second term of this sequence because it said start at term 2. But the first thing I add together. And then my next term is if I put in 3 here. So if I put in 3, I get negative 1 to the 3 plus 1, that's negative 1 to the 4th power. Negative 1 to any even power is positive. So this is going to be a positive number. And so I have positive, and then I have 4 to the 3rd power. We're putting in 3 for n. And so that's 64, 4 cubed is. And then let's go another term to put in 4 in here. Negative 1 to the 4 plus 1, that's negative 1 to the 5th. That's a negative number. And so I have negative, and then 4 to the 4th power, we're putting in 4 for n, is 256. Now we could keep going, but we're not supposed to on this one because this says add term 2, 3, and 4. 4 is where we stop. So there's term 2, there's term 3, there's term 4. This is it. That's all we want to add together here. So we're done. We just need to add these together and see what we get. And so if we add all this together, keeping in mind that those two are negative and that's positive, we get negative 208 is the sum of the first 3 terms, I guess the second, third, and fourth term, I should say, of that sequence. All right, so there's how we find the sum of a sequence. Let's see if we can go backwards now. This is the last thing I wanted to do is talk about if I have a set of numbers, how do I make it look like this? How do I put it in summation notation? So I've got the set of numbers that goes 5 plus 8 plus 11 plus 14 plus, and then do you notice this? It goes all the way up until we get to plus 3n plus 2. This one's kind of weird. We're going to have to think about this for a second. And so we know it's going to be in summation notation. So first thing I'm going to do is just put our big capital sigma. We're going to have that. Then we're going to have something under it, something above it, and something out here for the general term. Now this out here is kind of a dead giveaway of the general term. This is telling you to come up with these numbers, we did 3n plus 2. And so our general term is 3n plus 2. And then we just have to figure out what's the first number we put in there. Well, if I put in 1 in this, 3 times 1 plus 2 is 5, which means the very first number, our starting term, that we put in here was 1. Now we have to think about where did we end. Now if it just said this and stopped right there, our top number would be 4. Do you notice that's the first 4 terms? However, it keeps going, and there's no set stopping point to this one. Do you notice there's no set number of terms? It just goes out and says n. And so we're going to have to go until we get to a stopping point here. And so a lot of times what you do, if you have this n out here, we're going to change this variable, because this variable can be anything. So I'm going to do this. I'm going to make this k. And this is why we talked about just a minute ago that this variable can be whatever we want it to be. It's just a variable. And we're going to go until we get to n as the thing that we're putting in for k. All right, so let's think that through, because I feel like that's a little bit hard to think about. So we're starting where k equals 1 until we get to our last number we're putting in here is n. And so there's our summation notation for this. And so we're going to go k equals 1 to n of 3k plus 2. And it's still the same formula, we just used a different variable so that n could be our last thing that we plugged in. So there's how we come up with summation notation, and there's how we use summation notation to figure out sums of sequences. We're going to talk about in the next couple days how this applies to certain types of sequences and some general formulas that we can create when we have certain types of sequences that go along with this as well. But this is to get the foundation of what a summation looks like.